talking about the global nonlinear stability of Minkowski space for self-gravitating massive fields.
Thank you very much for the invitation. It's a great pleasure to be here. So I'm going to talk about the Einstein Equations and give you an introduction about that. So it will be elementary, and you are welcome to stop and ask questions. The basic question that I want to address here has been first treated by Christodoulou and Kleinerman a couple of years ago. I mean, more than that. It was in 1990, 92, around that time, so quite some years ago. And what they addressed was the question of the stability of Minkowski space. So Minkowski space is sort of as the simplest solutions of the Einstein equations in a vacuum, no curvature. And the question you are asking is that if you impose some perturbation, you prescribe some perturbation in Minkowski space, and you let these perturbations propagate according to the Einstein equations, what you wonder is what is going to happen to these perturbations. So the equation being hyperbolic, you expect waves to propagate at the speed of light, to interact, to decay, and if everything happens nicely, what you expect is that your space-time, being curved initially, will reconverge asymptotically back to Minkowski space. Okay? So this is a question that was addressed in the 90s by Christodoulou and Kleinerman, except that what they were able to treat was the case of vacuum spacetimes. And so even in the vacuum case, this problem is extremely difficult, it's very interesting. You have no matter, but still you can think of having maybe some matter field that has created these perturbations in the curvature, and you can study the evolution of the perturbations. So, but what I want to do here is to treat the case where there is some matter, and the matter has a mass associated to it. As you will see, what I really want to do is study the Einstein equations as a system of partial differential equations. So in the end, this is what it will be. I will take the geometric problem given by the Einstein equations, but choose coordinates, choose a gauge, and transform it into a huge system of partial differential equations, which are nonlinear. They are hyperbolic, so they have this idea of waves being propagated and possibly dispersing in time. And what I need to do in the end, in order to prove the stability result, is to be able to prove a global in-time existence theory for small solutions, because the solution will be close to Minkowski space. And I want to do that globally in a certain weighted subwave spaces. The weight have to do with some decay in space that you have to take into account. But more than that, they also will, as you will see, introduce the killing fields of Minkowski space as some important ingredient in the definition of the norms that you can control on your metric and on your matter field. So this is what we would like to do, and the motivation behind it is really to understand this phenomena of waves propagating in curved space. This is something, as I said, you can do in a vacuum case or in a situation where you have some matter. And you need to be able to exclude certain dynamical instabilities that have been, as I will mention soon, have been observed numerically, especially in presence of a massive fluid. You can have instabilities that may possibly create singularities, black holes, trap surfaces. So you want to avoid this phenomena, and what will play for you is the fact that you are only doing a small perturbation of the space, of your space-time, and you again hope that this wave will disperse. And dispersing, there's a lot of room, so this wave, maybe they start big, but they will become smaller and smaller as time evolves, because they move around in every possible direction. So this is a phenomena that you want to study. So of course the key part, the technical part, will be to prove a global existence for the Einstein equation expressed in certain coordinates. But of course, you have to be very careful that you have not chosen bad coordinates, and the final result that you are proving is really a geometric result, and you are really saying something about your space-time itself. So in the end, you need to check this property that what you have constructed, the development that you construct for the Einstein equations, is complete in the time direction.
So I'm just a little confused. You said we can interrupt.
Sure, yeah.
The thing is that the equations are, if you think of them in 4 dimensions, they're not moving, right? Like it's the whole future is there. It's just one space. It's not an evolution equation of any sort, right? So what should we think of? Should we think that outside some compact set, you're going to classify the pictures?
No, you have to think that you have an hypersurface. So in your four-dimensional space-time, you have an hypersurface, and you are going to prescribe, to make a prescription here. You prescribe an induced metric, and you will prescribe other quantities that I will mention in a minute. So you have to think that I know my space-time on one hypersurface, and I would like to know it in the future. And the Einstein equations are PDEs, evolution PDEs, when they are expressed in a correct gauge, and it allows you to determine the future from this. So the outline will be that, like that. I'm going to write the Einstein equations, so you will see where they come from. Just writing them from the Hilbert-Einstein functional. But in fact, I will treat 2 sets of equations. I'm going to treat the Einstein equations, but in the same time, I want to also address the same question for the theory of f of r modified gravity. And you will see what it is. So the scalar curvature will be replaced by a nonlinear function of the scalar curvature in a minute. So I will just formulate that, geometrically. Just write the basic equation, and not say too much. And then I will choose coordinates in order to really see the nature of the system of PDEs which is behind. And as you will see, the system is a coupled system of wave equations for the metric and Klein-Gordon equation for the matter field. And this is really the new aspect compared to what was done until these recent years, is that people before were looking at the Einstein equation in a vacuum, and they had wave equations. But the fact that you have now to treat the massive matter, to couple with the Einstein, with the Klein-Gordon equations, makes the problem even more challenging for reasons that I'm going to explain. Okay, so the next step will be to actually state the global nonlinear stability results. And I probably will have a little bit of time to state these results, not geometrically as it will be done in the first part here, but I'm going to state that in the so-called wave coordinates, where you can really see the spaces. You can see the spaces that you are using in the sub-F in the sub-F space. So normally I have a laser on this, but I need to push a button and wait a few seconds, and normally it works. Okay, so here we are. So the noun of the problem will be a Lorentzian manifold, and for me the topology will be very simple because it will be the same as Minkowski space. So I have R3 plus 1. So 1 stands for the time direction and 3 space directions. And if you start with the Minkowski metric, you can already see what I'm going to do. So I'm going to take this metric and perturb it. Right? So we just have coefficient -1 and +1 for this metric. And I'm going to perturb that and get a general metric with signature -+++, which will be close to this one. If you have a metric, I guess most of you know that you can define a notion of derivative, and the derivative is not simply the partial derivative in your coordinates, but you have lower order terms. Okay. The form of that is not very relevant just to explain the general ideas. So you have a notion of derivatives in your manifold, and if you differentiate once more, you also can define the notion of curvature, and especially the Ricci curvature is an object with 2 index with the same symmetry, the symmetric tensor like the metric. And for the moment, the only thing you need to have in mind that this Ricci curvature contains 2 derivatives of the metric coefficients, and it contains nonlinear quadratic products of one derivative of the metric. Right? You just know that this is enough for the next few slides. The scalar curvature is a trace of this quantity, so it of course will have the same sort of structure depending on second order derivatives of the metric. And I can now look at the Einstein equations. I know what is a Ricci curvature from a formula of this sort, so I can plug it in the left-hand side if I look at this definition of the Einstein curvature. So the Einstein curvature is just a combination of the Ricci curvature and the scalar curvature. In a vacuum, you would just put 0 on this side, and you would deduce that the scalar curvature is 0, and therefore the Ricci curvature is 0. So Ricci flat, these are the Einstein equations in the vacuum. But as I mentioned, I want to treat matter fields, so I also put a T alpha beta here, and I need to tell you what T alpha beta is. So it's the energy momentum tensor describing the matter, and so I show it to you in the next slide. So T alpha beta is a symmetric tensor, and it is given by this formula. So you take one derivative of your field, so it's a scalar field defined on the spacetime. It will be one more noun in addition to the metric. And you look at this quantity right here. So you have one derivative of the scalar field. This quantity is a norm, it's a Lorentzian norm of the gradient of phi. And then you add to that a function that has no derivative, just a scalar, nonlinear function of phi. And if you take phi squared times the coefficient, and this coefficient C stands for the mass of the scalar field. So if you do that, you get a definition of T alpha beta. You plug that in a previous equation, and you have the Einstein. So I will call it Klein-Gordon because I did not explain how you end up with this equation, but I will say that in a few minutes. This second equation here is a consequence of the Einstein equations using the Bianchi identity. So I mentioned that in the next slide. But at this moment, we can just stare at this system. Remember that R alpha beta was expressed as two derivatives of the metric. So it's a differential operator, partial differential operator, second order. This side, you can think of that as being lower order terms, because they have only one derivative. And then you look at the second equation, even though you may not know where it comes from, but you will see in a second. And this second equation is of a similar type, right? It contains the wave operator, which is defined by taking the gradients twice. It contains the wave operator for this unknown phi, plus lower order terms. Okay. So if you remove this capital U, this is just called the wave equation. If you take the U into account, you have a Klein-Gordon equation, especially if I take U to be, phi squared. This is really a linear equation, and you have a linear equation, with a box operator and a zero order unknown contribution from the unknown. Okay, so of course there are a lot to say about this equation, and what we are going to do is to make a choice of coordinates in order to actually see what is the type of PDEs that you have here. Right? So to see that it is hyperbolic, you need to choose coordinates. So I'm going to do that in a few minutes. Now the second set of equations that I want to look at comes from the so-called f of r modified gravity theory. So alternative theories of gravity have been introduced back, almost the same year as Einstein, just 2 or 3 years later. People realized that you could generalize the equations, and more recently, people, physicists or people making observations, believe that this generalization of the Einstein equation could be interesting to explain certain phenomena. The general idea is that you are not satisfied with the metric mediating the gravitational field, so you want to add some more freedom, so degrees of freedom to describe the gravity. There are hundreds of ways to do that, and I'm really looking at the simplest way to do that. But I think mathematically it has really a nice structure, and as you will see, it goes very well together with the analysis of Einstein Klein-Gordon that I just showed you. Right? So it makes a lot of sense to put them together for this analysis. So how it comes? So it comes by modifying the usual action functional and deciding that on top of the Lagrangian for the matter, you not only add the scalar curvature, but you add a function of the scalar curvature, and typically what you are really interested is to add a quadratic correction to it. Okay. So you can even kill that and just take f to be capital R plus kappa R squared. Kappa is small parameter. So as you will see very soon, I'm going to be interested in the limit when kappa goes to 0. Right? So formally you expect that modified gravity will go to the classical gravity. And this is a question that we will address. And I already mentioned, that 18, 19, 24, so there were a lot of people, physicists or mathematicians, looking at that. If you look for the critical points, if you minimize this function, formally minimize the functional, you can write the equation satisfied by critical points. And instead of the Einstein equations, you find a modification of it. So you find an equation that looks almost the same. N alpha beta is equal to 8 pi T alpha beta, except that N alpha beta is a modification of the Einstein tensor that I showed you before. And the modification doesn't look very, very nice at first, because instead of G alpha beta, for instance, here you have a coefficient depending on the scalar curvature. So this is really a product of two derivatives, function of two derivatives of the scalar curvature through the second derivative, of the metric, and then this is also two derivatives of the metric, right? So the product already is not very, very nice. But then you add even more term. You have to modify the scalar curvature in front of the metric in this way, and you have to. So this is even worse. You now have to take into account two derivatives of this function of the scalar curvature. So in fact, these modified equations are fourth order in G. Okay, but you will see, that they are not that bad, and I'm going to do basically two transformations to explain how they relate very closely to the Einstein-Klein-Gordon system. But for the moment, let's just look at this model to say, okay, we have another PDE, which now is fourth order instead of second order. Of course, if you choose f to be linear, you go back to the Einstein equation, and you can also check that vacuum Einstein solutions are also vacuum f of r solutions. Okay, but of course not the other way around, and not if you also have a matter field. Now, for the matter field, what I'm going to do here is to choose T alpha beta to be given by the same expression I gave you before, the same energy momentum tensor. Okay, so you may say, yeah, why not? We already took that before, so this is good. But in fact, in the physics literature, first of all, people call that the Jordan's coupling, and there is another way to couple the matter, the geometry, which is called Einstein's coupling, which, in addition to this expression, contains a coefficient depending on the scalar curvature. So I'm not doing that. And the reason is that if you do that, which is another model proposed in the literature, if you do that, it doesn't seem to be well posed. It is not well posed if you want to solve the initial value problem, right? So it looks physically like a model that maybe could be reasonable, but in fact, in terms of solving the initial value problem, even locally for a small time, this other choice of coupling would not be good. So now I'm almost at the end of the presentation of these two sets of equations, these two models. And to finish the discussion, I need to tell you about the Bianchi identities. The Bianchi identities are simply geometric properties of the curvature, which after some contraction, there are other versions of that, but this is a second or, it's a version of it, it's a contracted version of the Bianchi, the full Bianchi identities. And it tells you that the divergence of the Ricci curvature is essentially the gradient of the scalar curvature. Okay, and this is good because it exactly says that the Einstein tensor is divergent free, and this is in fact how the Einstein tensor, the reason why the Einstein tensor was defined, was chosen, and using the Einstein equations, you can deduce from this property that, yes, this is in the next line, you can deduce that the divergence of T alpha beta is equal to 0. Okay? And you may know that these are the so-called Euler equations for the fluid, for the matter, the divergence of the energy, a tensor. It can be regarded as a set of 4 equations, right? You have one free index, beta. So in general, it's a set of 4 equations to determine the fluid. You know, the mass density of the fluid and the velocity field of the fluid. So that would give you a set of 4 equations. But since our matter model, even though it's not so trivial, because it does contain this massive term, this is what I want to address, the matter model is rather simple. So in fact, these Euler equations for our matter model are equivalent to a single scalar equation, which is the one I wrote before, this wave or Klein-Gordon equation. Okay? And this is not difficult to see, right? If you take this T alpha beta and you compute the divergence, you will see that you get this guy times some vector field, and you get the condition. I mean, you get this equation. Okay, so with this we have all the equations, you know, and again, if you choose coordinates, you can write them. You get PDEs, second order PDEs. Maybe you don't know what to do with that, but at least you see, you see the PDE, the set of PDEs which is behind that. So remember that one issue that I really want to address is a convergence when the function f of r is going. So maybe let me show you again this action. So I want to address this question. I have a theory with just capital R, and I have another theory where I modify the scalar curvature with a quadratic term. So what I want to do, I want to prove global existence close to Minkowski with Einstein's theory, and I also want to prove global existence for modified gravity, and then address the question whether when Kappa goes to 0, these global developments are converging to the global developments of Einstein. Okay, so here we are, and before I proceed, let me say that even numerically, this is not an easy question, and it took years and years. I mean, it took 10 or 15 years before people actually agreed that Minkowski space should be stable in asymptotically, asymptotic flat space-time, close to Minkowski should be stable. And it was not easy to see numerically, because in an initial phase, when you put some perturbation of your matter, you can take everything. You introduce this perturbation. And what happened is that the matter tends to collapse and to produce, possibly to produce trap surfaces and then possibly black holes, right? But so the situation at the beginning, numerically, doesn't look nuts. But what happens is that there is an intermediate phase in the evolution of your matter, after during which there is a certain threshold in the mass density that makes the collapse to slow down, and eventually, if you try to construct such instabilities for arbitrarily small perturbations, but of course, if you take a big perturbation, you will create these singularities in your space-time. So I'm not talking about that. I'm talking of putting an arbitrarily small perturbation, and I wonder if this can still produce a singularity. Okay. So the answer to that question is no, but it takes a little bit of effort, and I guess this was one of the final papers on these numerical investigations. And to tell you why this problem is not so obvious, you could think of the case of asymptotically anti-de Sitter spacetimes, for which you have such instabilities. So you will take anti-de Sitter, make an arbitrarily small perturbation corresponding to adding some matter, and you will see that the effect of gravity is dominant, and the reason, the way to explain that is the matter is completely confined in this case, and there is no space for it to disperse, like I explained in the very beginning. So this is a phenomenon of dispersion, wave dispersion, that your PDE analysis should be able to exhibit. Okay, so I guess you probably all know that these gravitational waves have now been observed, so I guess I don't make a comment except to show this fantastic picture. So these are the observations by LIGO. There are 2 detectors in the US, and you superimpose the numerical results of 2 black holes colliding and emitting these gravitational waves. And the fact that these curves can be superimposed so nicely was really fantastic for people. So this was observed about a year ago and announced in February. Okay, so now we move to say the second topic, where now I know I have my equation but not written in coordinates. So I need to tell you what I do with that, right? So it's second order, no specific PDE type. So what you do, and this is a trick that comes from Dr. I would just say maybe Dr. used that to analyze the Ricci flow. It was called harmonic gauge, but in fact these coordinates were stop me if I'm saying something wrong. But
I would say it was the other way around. People did this.
Yeah, I was going to say that it was.
The Turk was the analog 50 years later or something.
Yeah, I know. I was going to say that. So it was even by Einstein himself. Yeah. So these coordinates were used by Einstein. I mean, introduced by Einstein himself, even though he did not understand really what was going on, of course, at that time. But he was looking at a linearized equation and using these coordinates. But you're right, just somewhere in the field we know it as a Dotter trick. Sometimes the history is a bit complicated. So it was introduced by Einstein, used by a number of physicists after that, and the first time it was used to prove a mathematical theorem was by Yvonne Choquet-Bruat in 1954. So she proved the first result of local existence for the Einstein equations using these coordinates. So why is these coordinates good? They are good because they really give you the type of the equation. So they allow you to say that the Ricci curvature, the dominant part, is a wave operator applied to G alpha beta. Okay, so originally, it was really a combination of second order derivative of various components of G alpha beta. So you have killed the components that some of you didn't like, and you made the operator to be exactly the wave operator that you like. Now, so what happened with that? So if you plug this, if you choose these coordinates, what you are going to get is a second order system of, so there are 10 nonlinear wave equations for the metric. And this is coupled with one Klein-Gordon equation for the matter field. That's the structure that you are getting. But this is not it, because you also have constraints. When you want to solve this problem, impose certain initial data, there will be certain constraint, Gauss-Codazzi constraint on your data, and you have also to supplement that if you want to formulate an initial value problem. Okay. So I'm not going to say anything about these constraints. And now this is what you get, right? So I think from what I said, you can see now that the Einstein equations are taking this form. A wave operator of G alpha beta. I put a tilde, I guess it doesn't matter so much at this moment, but it's a modified, but for good reasons of this geometric wave operator that I wrote before. You have quadratic terms in dg, which I'm going to write, because for me this is very important. I want to prove global existence, and I have a system where one part, the wave part here, the Klein-Gordon part, is if the metric was fixed. This is an easy equation where waves would be propagating, and you can prove global existence if you have fixed the metric, right? But of course, in our case, the metric is the unknown of the problem. So it comes in defining the operator. And it comes, even more important, it comes as a source here of quadratic terms. And if you think of, if you have never seen any nonlinear hyperbolic PDEs, you can even think of just an ODE of a Riccati type, where you have, maybe you have one derivative, say that will be one derivative of dg, say, and the other side will be quadratic in dg, right? So it's a sort of Riccati equation which we know is going to blow up, to produce singularities in finite time. So it's really unclear in this form that we are going to be able to prove global existence for this equation. These are the terms that I wrote before, and this is the Klein-Gordon equation that we have. Okay. So now, why should we still be able to prove a global result for that? So the reason is in the structure of these nonlinearities. So these nonlinearities, really, there is nothing like a Riccati equation hidden behind that. And the reason for that is that these nonlinearities have a very special form. And if you write, and I will show that in the next slide, so it's a bit ugly, but maybe it's good to just have a look at it for a minute. But before I show you this ugly formula, I just want to say that all the terms will be on this form. So there will be either a combination of certain quantity, uv will be components of the metric. And so either I will compute, d alpha of u, d beta of v minus d beta of u, d alpha of v. So this is one sort of combination you will get for the nonlinearities. Or you will take the same u, but you will contract with a metric. So you can really think of that as being, if you write this in Minkowski space, you would just be looking at something like dtu to the square plus maybe dx j u to the square. Right? So you will be looking at a quantity like that. And so both of these quantities have very nice constellation property. Okay? So I'm going to compute an energy associated with this. This is a wave equation, so there's a notion of energy. And I want to show that this energy is globally controlled, globally bounded. Right? And there is a risk for this term to actually increase the energy in some uncontrollable way. And it will not be the case because of the structure, the fact that all these terms are only like this or like that. Okay. So, now this is, in fact, this is only part of the story. So I need to give you one more important idea at the end of this slide. So what we do, if we really want to look at these terms, we now need to know how the Ricci curvature is defined from the Christoffel symbols. It has the structures that I mentioned before. And we need to know how these Christoffel symbols are expressed in terms of the metric. So if you use that, and you impose the wave condition that I wrote before. So you remember, maybe let me show you just a second. So the wave condition is giving you certain linear combinations of one derivative of the metric. Okay, so you have four relations like this. So these are constraints. Maybe I should also have emphasized that these are constraints that you impose initially and will be propagated. And they allow you to manipulate your system of PDE, right? If you can use that to somehow simplify and arrange the nonlinearities in your system. So this is what you get. You get that R alpha beta is a wave operator G alpha beta plus two types of nonlinearities. So Q and P. Q is what? Q is precisely terms like I explained to you. So you look, for instance, at the first one, and you see that there is a contraction with delta prime of this. And then you look at the second term, and it has a second sort of form that I showed.
Okay. Should we think that these things are preserving some kind of compact, some symmetries of some compact sets so they don't blow up or something?
No, there's no symmetry. It's not compact. I will write decay conditions. The metric will be asymptotically flat, so it will become very close to Minkowski far away. So
they look like Lorentz transformations.
Second, it looks
they look like Lorentz-like transformations. The symmetries, the skew symmetry. It's nothing like that.
Maybe, but no, I don't see that. So this is not the end of the story. So as you can see, I wrote a Q, but I also wrote a P, right? So what is P? So P, unfortunately, does not satisfy this null condition, this good decay condition. Okay? So we have a system that looks like a nice wave system with nice null terms, but it is not like that. It is not like that because there are terms that I call quasi-null, and earlier they were by Lindblad-Ronienski, they were called weak null terms. And they look similar, but unfortunately they don't have the nice null structure. And so the way to treat that requires, this is a significant part of the analysis to understand how you can control these terms they would not create a rickety type of phenomena in your system. Okay, and maybe I will say a few more words later about that. I mean, one idea is that you need to use again the gauge conditions. You have not maybe worked enough in understanding the structure of this step. So using the gauge condition once more will allow you to give some simplification, and then in the energy estimate, you really have to be very careful to make sure that there is nothing like feedback phenomena where some components of the metric will increase the energy, and maybe this will go back to the components and eventually make it to blur. Right? So this is not the case, but it's really a significant part of the work. Okay, now the modified gravity equations are fourth order, no specific PD type. And before you proceed with introducing wave coordinates, you have first to do two things. First, introduce a conformal transformation of your metric. So I'm going to define G dag to be G multiplied by a scalar factor, which is a function of the scalar curvature. Okay, so it's also the unknown of our problem. So you have a nonlinear function of your unknown that you use as a conformal factor. And if you do that, so you may know this formula to transform Ricci curvature of a metric into the Ricci curvature of a conformally equivalent metric. And in this identity here, where rho has been defined to be essentially like the scalar curvature, and remember that kappa was my coefficient here, so I'm using this definition here. So this formula involves two derivatives of rho, through that. And so if you use this transformation, you can see that the fourth order terms are cancelling, and you end up with a third order system. Okay, so from a fourth order system in the original physical metric, by using this conformal transformation, I get a third order system in a non-physical metric G dag. So this is one transformation you need to do. And the second transformation, to go from a third order system to a second order system, which is what I really want I want to get the same structure as the structure I showed you. So how do I get the second order structure? I get that by deciding that rho itself, my scalar curvature transformed in this way, is an unknown of the problem. Okay, it's normally a function of the metric, but I want to forget that. I want to forget this formula, look at the equation satisfied by rho, and use it as an evolution equation of its own, and forget about the connection between rho and the scalar curvature. Okay, so you will see how it goes in the next slide. And to finish, I introduce the wave coordinates, but it is, of course, in this new metric G dag instead of the physical metric. So if you do that, what you have is a second order system which has one more equation to the previous system, and this additional equation is an equation for the scalar curvature. And you will see the structure that it has, and it is in fact another Klein-Gordon equation, right? So we will get the wave equation for the metric, and then two Klein-Gordon equations, one for the matter field and one for the space-time scalar curvature.
Are you going to be able to ensure that f prime r stays positive? Or
yeah, because it's a good question. But we are doing small perturbation around
zero.
Around zero. So this is not an issue.
So are you including an r cubed term, or are you assuming that f is just quadratic, has only the quadratic?
No. It's anything which is there could be higher order terms. It doesn't matter in the series. So it doesn't have to be exactly quadratic.
I didn't understand the answer to my question.
Yes.
So it's a small perturbation around zero.
Yeah.
But what you need
so the scalar curvature will be close
to be positive to.
So this quantity is 1
1
plus
plus
1
kappa
plus
r. Say 1 plus r, and r is small.
and kappa.
And kappa is small.
Oh.
So we have to make sure that there isn't any blowing up, otherwise this transformation will break down. But I
Of
guess
course.
after the fact, it'll be okay.
Yeah, close to okay, let me finish with this. So the structure is more involved than what we had with Einstein Klein-Gordon, because we have this additional relation, which again I can prove that if I satisfy this relation initially, it is propagated. The same, I mean, the same sort of tricks that you do all the time. You only impose all these algebraic conditions initially, and you know that they will propagate. So rho will be, I will forget about this relation in my main analysis, and I just know that if it is satisfied initially, it will be preserved. Okay, so here we are. We have a system for the metric. So what is new now?
That would be initially a statement about small times, right? So you would have...
No. This would be global in time. Right? You can, the way it is done is that you write the system PD and you do first a local existence result. Right? So that's, I mean, in this story, that's always what you do. So first you check these properties, but then in terms of preserving the constraints, this is a general statement. So for any time, you will preserve the constraints.
As long as the solution still exists. Which is
of course, yeah.
It's kind of a circular argument then, isn't it?
Of course, I mean, the hard part, this is very soft to prove that this is preserved. This is very easy to do. The hard part, you're right, is to prove global existence. Make sure that the solution does not blow up and exist globally. Okay, so now I need to show you the structure of the system. And the structure will be wave for the metric, Klein-Gordon for the matter field, and Klein-Gordon for the scalar curvature. So this will be the main part. And on the other side, you will get lower order terms. So they are a little bit ugly, but if you look, for instance, at the first line, the only thing new here is the exponential. If you take kappa to be 0, this is exactly what I wrote before for Einstein Klein-Gordon. Right? You see that. But in this equation, I have one more term that comes from the scalar curvature. And I wrote it in this form. It's very similar to what you had already for the matter field, but now think of rho as being, scalar curvature. So you have this part, and you have also quantities that has no derivative in rho. And I just wrote it like this. It's a certain function which is quadratic in rho. So everything will be small here. The metric close to Minkowski, rho will be small to close to 0, and phi will be close to 0.
Is rho actually the scalar curvature of G diagonal?
Yeah, it's a bit more complicated, but it's a function. Maybe I could write it here. So I think it's 1 over kappa log and f prime of r. Okay, but you can observe that this converges to r when kappa goes to 0. Okay, so I can think of it as really being the scalar curvature. So these are the equations for the metric. Then you have the matter field. So Klein-Gordon. So before we had Klein-Gordon equals 0. And again, if you take kappa to be 0, this would be gone. Kappa to be 0, this would also be gone. Here you can see there's a product of gradient phi, gradient scalar curvature. And so one more equation, which is this one, with lower order terms. And the last equation is a Klein-Gordon equation, like I said already. But it has really a different nature, flavor, compared to the Klein-Gordon equation for the matter. And this is why I like, I like the system and the structure, the analysis that you can do behind, because for the first equation, it's natural to take C positive for massive fields and C equals 0 for massless. Right? And you have a certain singular limit, which is not too singular, but still it's not direct to study that, because large time behavior when C0, C not 0 is really significantly different, and the properties are significantly different in terms of symmetries. But the second equation is very different. It looks the same, right? But it is very different, because I'm interested here in two limits. I'm interested in the case where kappa is fixed, and I'm interested in the case where kappa goes to 0. But kappa going to 0 is going to kill the principal part of this PDE, which is not something you like to do, right? So I'm going to return to that. So you have wave gauge conditions, you have the curvature compatibility, as I call it, between rho and this expression of the scalar curvature that you can recompute if you know the non-unphysical metric. You remultiply by your conformal factor and so on. And you have to check this relation. And all three of these are propagated from assumption that you only put on the Cauchy hypersurface, the initial hypersurface. In a limit when kappa goes to 0, I already explained, the conformal metric will convert to the physical metric, and this is interesting. So So this quantity, I mean this convergence here, you can see it formally from this line here. So if kappa is 0, this is gone, and this exponential becomes 1, and you can show, you can see immediately formally that this relation is true, and therefore you see that you see the formal convergence between modified gravity to Einstein gravity by just comparing the equations. Okay. So the goal now is to prove a global existence result. For that, in fact, two results. You want global existence for Einstein Klein-Gordon. You want global existence for f of r gravity, and you want to show that when kappa goes to 0, the global solutions of one system are converging to the global solutions of the other system. So we arrive to the third part of that. So this may be a kind of summary of the technique behind. I'm not sure I will have time to show you much of the techniques, but we have the PDE system. We need to prove global existence. So the difficulties are, first of all, we don't have invariance by scaling because of the Klein-Gordon terms, both for rho and phi. There is no invariance by scaling, and this means that there are killing fields of Minkowski space that you can no longer use. And for instance, if you want to define an energy to control your system, there is an energy that you define from the wave operator, but then you want to define higher order energies. And to do that, you apply killing fields, you differentiate, if you like, your system of PDEs by using these vector fields to boost possibly the scaling field. But here I cannot do the scaling field. So what this means is that if I define some energy, before the scaling field was used to define the energy, so if I can no longer use it, I get a weaker energy, a weaker control on my solutions. So I need to be able to do that. And another way to look at the problem is that the fact that you have now Klein-Gordon equation is really very different because the time asymptotics are different. For wave equations in 3 + 1 dimensions, they decay like 1/t. But Klein-Gordon equations decay like t to the -3/2. So these are, very different behaviors in terms for analyzing the system. So are we going to have enough decay of these nonlinear interactions in time? And this is really the coupling between the geometry and the massive matter terms that is this coupling that is producing all the problems. So in short, in just a few words, what you have to do is you have to revisit a number of notions that were introduced earlier by Kleinerman, Christodoulou, and a few other people, and make sure that all you write in terms of pointwise estimates or L2 energy estimates are sharp. So they will not be completely sharp, but there will be typically some loss. If I can show the estimate, you will see that. But they are essentially optimal in terms of controlling the energy and the pointwise behavior of your solution. The quasi-null structure of the Einstein equations, I mentioned that, so I told you a little bit about that. There is this idea that you don't want some feedback that comes from the bad, not null terms to get some feedback and amplify your energies in an uncontrollable way. So let me try to state now the result more, at least geometrically. I already mentioned how the problem should be set. It gives you the geometry, so not only the induced metric, but also we need the second fundamental form that will tell us how this initial slice is curved in the spacetime that you want to construct. We have matter fields. Phi 0 is a matter content, is a mass, if you like, of how much mass you have, mass density initially on your hypersurface, and phi 1 tells you how fast it is moving, where it goes. So you need these two data to describe the matter content initially. And we have data that are close to Minkowski. I already mentioned the work of Schoke-Breuer. I mentioned Christodoulou-Kleinerman already a couple of times. Their proof was fully geometric, so rather different from what I'm explaining today. But the proof that was done for massless scalar field using wave coordinates is the one by Lindblad Ronienski in 2010. And this was really the first global existence result in wave coordinates, I should say. And this was surprising because because there was some earlier work, I mean, years before, by Choquet-Bruat, and she was saying that this gauge might be unstable. And by defining an approximation scheme to attempt to construct solution, she was claiming that there is precisely this sort of feedback that makes control of the energy impossible. So Lindblad and Wodniewski were the first able to do that for massless fields and using a foliation of the space-time which is asymptotically flat. Most importantly, all these proofs were using all the killing fields of Minkowski space. Okay, so the challenge that I had here, and this is my work with UMA, was not to rely on the scaling field, and the way to proceed, it turns out, was to introduce a foliation of the space-time. And I have a picture, maybe a bit later, I can show you some pictures to illustrate how my foliation is defined. But I have a different foliation, and the idea of this new foliation, asymptotically hyperboloidal, is that somehow it fits better with a light cone. So if you have a perturbation, this perturbation will typically propagate along null rays, and so the light cone is something essential in the problem. And you want to have a nice, I mean, a foliation which is give you a lot of information about what is going on near the light cone. So I introduced this hyperboloidal foliation method 2 years ago, and this was really the key to tackle massive fields. And in fact, in the end, it turns out that it also produced a slightly simpler proof, or more clear conceptually the proof, even for the case of massless field. Now, to formulate the problem, you have to have in mind the positive mass theorem that says that, if you want to introduce a perturbation, you cannot perturb Minkowski by saying I keep Minkowski outside. So maybe I go a little bit into answering your question. So you could say I just want to perturb Minkowski, so I could take Minkowski outside the ball and make a perturbation, locally, and study that. But it doesn't make any sense, because if you would have this setup, you could conclude that your space-time is actually exactly Minkowski by the positive mass theorem. Okay. So you need to have something non-trivial, some non-trivial curvature at infinity. And what you can do, if you want a simple setup, you can decide that your metric is exactly Schwarzschild outside a especially compact region. So that's an admissible set of initial data. But more generally, what you want to do, you want to assume that your metric approaches Schwarzschild near space like infinity. And the way to say that is to say I have my initial metric, induced metric, and I will look at Schwarzschild metric and allow for a perturbation which has to decay in a certain way, faster than the 1 over the 2m over r term that you find in the expression of the Schwarzschild metric. The second fundamental form, it would be something similar with one more r, and the scalar field has also a decay which is slightly faster than 1 over r. So this is what we are assuming for the initial data set to express how it, how it is close to Minkowski. Of course, this doesn't say everything, because you also need, it says how it decays. It decays like Schwarzschild with a small ADM mass coefficient. If you take m to be large, of course, this is not, not close to Minkowski. So you are assuming m to be small. And this is the result. So we have 3 theorems. The first one is to say, I consider Einstein massive field, the antimassive field system, with an initial data set, which is asymptotically Schwarzschild, and close to Minkowski, in a way that we need another statement later to explain that. And it satisfies the Einstein constraint equations. And I prove that this problem admits a global hyperbolic Cauchy development. So I can solve the Einstein equations and get a development where the space-time that I'm getting is really only determined by my initial data set. This space-time is foliated by space-like hypersurfaces, which are chosen to be asymptotically hyperbolic. Right? So even though I have a picture that I will try to show you, even though initially my hypersurface is asymptotically flat, that's how you want to set the problem. In fact, the foliation, it's good for the analysis to introduce a foliation which is asymptotically hyperbolic. Again, because of these reasons that in this way I foliate the behavior, what is going on near the light cone more precisely.
Your initial data set, it's on R3, so what's happening in the area around the black hole? I mean,
Right, but it's really only, it's an asymptotic.
You're saying it's asymptotic on the,
Yeah,
on the exterior region, but you don't care about.
Exactly, this is only for R bigger than, 3M, say, right? So it's just a statement about its behavior, but in a middle, I mean, everything's smooth. So in a proof, for example, in a proof, what you do
don't
is
need
that
any interior estimate.
you have interior and, outside, inside estimates, right? Interior, exterior estimates, where you put together Schwarzschild, in the large, and Minkowski. Yes. So, okay, so I guess that's, should be clear. And then there's a second result, where maybe I don't need to say, especially given the time constraint, more. The only thing is that instead of 5051, I have 5051, and then I need to prescribe the scalar curvature, space-time scalar curvature. I need that in the theory. It's really a higher order theory. So I need more initial data. I need the scalar curvature and the time derivative of the scalar curvature. But otherwise, the result is the same, the proof is the same. And now the third result is a convergence when kappa goes to 0. And I already pretty much explained what was going on. We had an equation for rho. And formally, we realized that rho should converge to that. And so now this is a theorem. The theorem is telling you that this is true. The Cauchy development of modified gravity when kappa goes to 0, which means that this function f is converging to the standard scalar curvature function. These Cauchy developments are converging. At least this is true in every bounded time interval, or any time interval you want. But there is a so that's how the statement is done, in the sense that I can specify quantitatively in weighted Sobolev norms. So these convert to Cauchy developments of Einstein gravity theory. Okay, and I may have just 2 minutes, right, to say just a few words about the last slides. So this is maybe a picture to try to explain that I have an interior region which will be the future of one hyperboloid here. This is a picture in Minkowski space, just to give you the idea. And I have really 2 regions in this foliation. So there is the interior region, foliation of the interior region, where all my slices are asymptotic to the same limiting light cone, and they approach the same sphere at infinity. So I have somewhere here, I mean the picture, I could make maybe a better picture, but there is one light cone somewhere here, and all of these are asymptotic to a single one. And then outside this, what I'm doing here, I'm taking slices that are also asymptotic hyperboloid, so they go to a light cone here, but this is a different light cone. Okay, so as you move in this direction, you converge asymptotically to a different light cone, and this becomes more and more flat as you approach the initial time. Okay, so this is a foliation made of asymptotically hyperboloid slices, which are in a singular way, but they are converging to an asymptotically flat slice. So now let me try to say in maybe 1 minute that I have norms. I told you that I need to define norms, and so the norms I can only use very few killing fields. And so the killing fields that I'm using are the boost on the hyperboloids. All these hyperboloids, with different geometry. I use that to define my norm, my energy norm. And then, if I want to do something in space-time, I also use a translation in space and time to differentiate. And I call this norm, there is a norm which is h, and it depends on a specific hyperboloidal time on my slices. Or I can define an energy norm, which is a sup of this between two slices. And so using that, if you understand that, these are the results. So I just restate as a result of stability, but now using the wave coordinates. So you can see specifically that I have my initial metric, the Schwarzschild metric. I mean, we are here only looking at one. We are here looking actually at the future. There are 2 regions. So the statement here is concerned with the future of one hyperboloid. So I'm now assuming, so it's a little bit different setup because this is only half of the problem. So I'm now assuming that my initial data set is asymptotically hyperboloidal. satisfies the Einstein Hamiltonian momentum constraint, together with some smallness condition that I didn't write before. I mean, I couldn't write them because I didn't have specific coordinates. So now I'm explaining you how I define the smallness condition. And there is this norm that you can see what it is, because I told you that this Hn was defined by using the boost. So that's what I'm assuming on the initial data. And then I can prove that this is preserved in my space-time, and I have a similar energy where not only for this energy I'm using the boost on every slice, but I have also used the translation in order to get some control in time, if you like. So the statement is that if this energy of order n, for large n, is small, then it's going to remain small in this way. But there is a small growing mode in that. So the energy, the fact here is that the energy is allowed to grow slowly. S is, again, is the hyperbolic at time. Delta is an arbitrarily small parameter that I put here. And I prove, I prove that these energies are slightly growing, but there is a control, uniform control of the metric behind. So I could have written that as well, but we can control that the metric, the Minkowski metrics, they are closed uniformly, and this is why we can prove that the space-time construct is heuristically complete. So similar theorem for the theory of modified gravity, depending on Kappa, and there is a theorem that I will not show you that tells you that when this parameter Kappa is going to 0, I have a completely uniform control of my energies here. Everything is going now to depend on Kappa, but when Kappa goes to 0, slightly more complicated estimates than this one are actually converging to these estimates that you have on this slide. So you have a proof of global existence for Einstein, modified gravity, and convergence for one to things. Okay, I'm sorry that I went beyond the time.
So, are you saying that you have good control of the future development, but not with backwards in time? So you've got a choice of these hyperboloids that don't go to. Do they go to just flat R3 at some time?
I mean, you really want to solve in the future. I mean, this is a hyperbolic, so you can solve both ways. It doesn't matter. But what I really do is that either I solve from an hyperboloid. Maybe I should show the picture. So So what I'm doing here, what I show you is a situation where I take this extreme hyperboloid and I solve in the future. And then the other part of the construction is to start from asymptotically flat data here and to solve in this region. So first I solve here, and then I solve in the other part. Okay, I will not do it backwards.
So for the result as a whole, the initial data set is on an asymptotically flat hypersurface?
That's right.
That's where it starts?
That's right. Initial data set are given here on a line that I didn't write here. So
that line looks like it's not asymptotically flat though. It looks like it's...
Well, I mean, I think I should add a line, a straight line here to make it more.
But these things are all asymptotically null, yes?
But I guess what you're saying is that you have two regions.
Right.
You have certain estimates, and then afterwards, when these things grow faster, you have some other reason why it's under control.
But each of these hypersurfaces is actually asymptotically null. You're just drawing it on a scale where...
Yeah, they all go to an icon, right? All of these, in the interior, they all go to the same icon, and outside, they convert to a different icon. This is what
but the theorem itself can be phrased where you've taken an asymptotically flat initial data hypersurface,
Yeah.
and then you have global.
Wait.
Given such initial data on an asymptotically flat hypersurface, you have global at distance and time.
That's right.
Okay.
Maybe I can show the geometric result was really stated in this way.
Right.
Asymptotically, asymptotically flat, and the statement is that we construct an asymptotically hyperbolic foliation.
These foliations have any particular geometric properties on the solution itself, or?
No, it's really not. It's not geometric. It's really based on using these coordinates, and so asymptotically, it has a nice geometry property, but in between it's not related. It's not the geometry.
So like small like CMC or
No, it is not. It is not. And it's not necessary for this existence result.
Is it possible to think of these f of r equation as regularization of the classical equation for a special f, and then you say prove a large data existence result for the f of r equation, take the limit as kappa goes to 0, and then get a corresponding result for the Einstein equations?
That's not what I've seen here. I mean, what I've seen is that this theory is adding one Klein-Gordon equation. So it's not introducing any regularization.
Any other questions? Let's thank the speakers.
Thank you.